Hello, chemistry students. This is your Unit 11 lesson on basic gas laws. So, what are four variables you could measure about the gas in this hot air balloon? Okay, you could measure its volume, you could measure its pressure, you could measure the amount of gas, and in chemistry we use moles, and you could measure the temperature. So the basic gas laws relate these four variables to each other and allow you to predict if you change one of the variables, what happens to the other variables. So let's launch into this. So the first basic gas law is called Boyle's law. And in that law, we are going to look at pressure and volume. What happens to pressure and volume when they change? Now we're going to assume the other variables are held constant. Temperature and amount are held constant. So as you can see in the picture, if you increase the pressure on a contained gas, and the way they're increasing in this picture is just by adding weight to it, you'll notice what happens to the volume. It goes down. So an increase in pressure causes a decrease in volume, and this is called Boyle's law. So in words, Boyle's law says this: the pressure of a gas is inversely related to its volume as long as the temperature and the amount of gas stays constant. And it's called Boyle's law because it was first proposed by the scientist Robert Boyles. Now, here is the graph, and it is an inverse relationship. As one goes up, the other goes down. So if you look at this, if we increase the volume, you can see that the pressure is going down. And conversely, if we decrease the volume, you can see the pressure is going up. So pressure times volume is always going to give us a constant, and in order to have that constant, they're going to have to vary inversely because it's a multiplication. So the equation for Boyle's law is this: the initial pressure times the initial volume should equal the final pressure times the final volume. In other words, pressure times volume gives you the same number. So as long as I give you three of these variables, you should be able to solve for the fourth. So P1V1 equals P2V2, Boyle's law. But again, this is true where temperature and amount of gas are held constant. This is called an inverse relationship. As one goes up, the other goes down. So here is a problem to solve with Boyle's law. If the initial pressure of a gas is 2.4 atmospheres and the initial volume is 2 liters, what will the new volume be if I decrease the pressure to 0.8 atmospheres? Now again, here is your equation, and I've given you 3 of the 4 variables. Do analyze this for a minute. We have atmospheres here and volume here. Those are the initial. And what we're going to do is we're going to decrease the pressure. Notice that it's going down from 2.4 to 0.8. Now, since this is inverse, if we decrease the pressure, what's going to happen to the volume? Go ahead and plug in and see what answer you get, and then only maybe pause the video while you do it, and then see what my solution is. Okay, so I have plugged in for P1 2.4 for the atmospheres, that's the unit of pressure, 2.0 for liters for volume. The new pressure is 0.8, and now I can predict what the new volume is going to be by solving for V2. And V2 will be 6 liters. Now think about this. It's inverse. So I cut the pressure to a third. I divided it by 3. So if it's inverse, what did I do to the volume? Well, I multiplied it by 3. So that's why I have 6 liters. I cut the pressure a third. That means that the volume will actually increase 3 times. Okay, the next law is called Charles' law, and this is the one that relates temperature and volume. So when temperature and volume change, you can use Charles' law to predict. But of course, you have to remember that pressure and amount will remain constant. So if you look at this picture, you can see we have a very cold gas and a very warm gas. When we increase the temperature, you can see that the volume also increases. So you increase the temperature, so does the volume. So here it is in words. The temperature of a gas is directly related to its volume. As the temperature increases, volume increases. Pressure and the amount of gas, of course, must stay the same. So here is Jacques Charles. Now, why was he so concerned about gas laws? Well, he was a very famous hot air balloonist, and he actually set quite a number of altitude records back in the early 1800s in his hot air balloon. So he would really need to understand the relationship between temperature and volume. Okay, it's a direct relationship. As you see, as the temperature goes up, the volume goes up. Now, I want to show you something very important. For all of these gas laws, we need to use Kelvin, absolute zero, as our temperature scale. We want zero temperature to mean no temperature, just like zero volume means no volume. So anytime you have a temperature in Celsius, you're going to have to convert it to Kelvin in order to use the gas law. Okay, just keep that in mind. So notice how this is different than the inverse relationship of Boyle's law. This is a direct relationship. As one goes up, the other goes up. So again, we're going to give you 3 of the variables, and you'll have to figure out the 4th. Again, V1 over T1 equals V2 over T2, where the pressure and amount of gas are held constant, and T is always in Kelvin, a direct relationship. Okay, here's the practice problem for this one. Again, you may want to pause the video and try it out before you look at the key. All right, so here's the key. So our initial temperature is 400, that's why it's here. Our initial volume is 2, that's why it's here. We decrease the temperature to 100, okay? So since this is direct, we're decreasing it. What's going to happen to the volume? It should also decrease. And we're decreasing it to 1/4 of what it is. So the volume is also going to be 1/4 of what it is. Again, you've got all of the variables. You'll just cross multiply and you will solve for V2. And V2 would be 0.50 liters. Next law relates pressure and temperature. Gay-Lussac's law. Pressure and temperature change, but volume and amount stay constant. So you can see in here we have a temperature increase, but we're keeping the volume constant. And you can see that as the temperature increases, the pressure also increases. The particles are moving faster, and there are more collisions, and that's what pressure is. So in words, it says, if the temperature increases in a container of fixed volume, the pressure will also increase. Now, this is a picture of Gay-Lussac. He was also really a competitor of Charles in terms of trying to set high altitude records with their hot air balloons. So again, understanding how temperature, pressure, volume, amount all interact with each other would be life or death for a hot air balloonist. Again, Gay-Lussac's law is direct. As the temperature goes up, the pressure goes up. And here's the equation. You can see it's a direct relationship. Temperature goes up, pressure goes up. You'll be given 3 of these, you'll solve for the 4th. Again, with Charles's law, as with Charles's law, this temperature has to be in Kelvin. So here is our problem. The initial temperature of a gas is 200 Kelvin, and we're going to assume 3 significant figures here, and has a pressure of 760 millimeters of mercury, again, assuming 3 significant figures, and it's heated to 300 Kelvin. What will the new pressure be, assuming amount and volume are held constant? So we're increasing the temperature. What do you think is going to happen to the pressure since it's direct? Okay, pause the video, plug in, see if your prediction is right. Okay, so here is the initial pressure. Here is the initial temperature in Kelvin. Final pressure. You'll notice we are increasing the temperature. So notice what happens to the pressure. It also increases. And you should have gotten 1,140 millimeters of mercury. Okay, Avogadro's law. This looks at the variables of pressure and amount, and the volume and temperature will stay constant. This is also a direct relationship. It's named after Amedeo Avogadro, really much longer name than that, and this is the same Avogadro from Avogadro's number. Here it is in words. If the amount increases in a container of fixed volume and temperature, the pressure will also increase. Here's the graph. Again, if we look at the picture here, we've got fixed volume. If we start cramming more particles in there, well, then the pressure will increase. It gets more crowded, there are more collisions, and remember, that is what pressure is a measure of. It's a direct relationship. So here's the equation. A direct relationship. As one goes up, the other will also have to go up. And again, this is where the volume and temperature of the gas are held constant. Let's try our practice problem. So if a container has 4 moles of gas at 1 atmosphere, what will its new pressure be if 2 moles of gas are added, assuming constant temperature and volume? So again, here it is. You have to be a little more careful this time. Watch very carefully. Let's see if I trick you. Think about what the initial number of moles is versus what the final is. Pause the video and see. Again, you're making it more crowded, so what should the pressure do? So again, if you look at this carefully, the initial pressure was 1 and the initial amount was 4. Now we added 2 more, so the final amount is 6. Okay, not 2. And therefore it's gotten more crowded and the pressure will go up. And again, you will just cross multiply to solve for the new pressure. Now, in practical terms, it's often difficult to hold any variables constant. And when there's a change in pressure, volume, and temperature, there's something called the combined gas law. Now, it does assume a constant amount, but think about a balloon ascending. It's going to have changes in both pressure, volume, and temperature. So the combined gas law is like smooshing all the gas laws together. So P1V1 over T1 equals P2V2 over T2. Notice if we keep the temperature constant, we've got Boyle's law. If we keep the pressure constant, we've got Charles' law. And if we keep the volume constant, we have Gay-Lussac's law. So we sort of push this all together. This is a fun one to solve. Now you're going to have to be given 5 of the variables so that you can solve for the 6th. So let's try one of those. So if a balloon ascends from standard temperature and pressure to higher altitudes, its new pressure is 720 millimeters of mercury, and its new temperature is minus 5 degrees Celsius. What is its new volume? Now be careful. You need to know what standard temperature and pressure is. That's going to be that initial values. So do you know what that is? Now the new pressure is 720 and it says the new temperature is minus 5. What are you going to have to do to Celsius before you can plug in to this equation? So give it a try and let's just fill in the values. Remember what standard temperature is. It's 760 millimeters of mercury and standard temperature is 273 Kelvin. So you had to remember that. Now the volume that you start with is 3. Now it says that the new pressure is 720. So the pressure actually goes down, okay? But the temperature also goes down. Notice, where did I get the 268? Well, that's my conversion of Celsius into Kelvin. Now, you got that big equation to plug into. Can you do it and solve for V2, the new volume? So here it is. You got to fill everything in. So the first pressure is 760, 3, and the various temperatures. Now you're going to solve for V2. So that's what I have down here. So easiest thing to do is solve for V2 because that's what we're trying to get to. So if we cross multiply, we're going to get V2 equals P1 V1 T2. Notice right here. And then you're going to have to divide by P2 to get to isolate the V2. So again, we're going to plug in these values. P1 is 760, V1 is 3, T2 is 268, T1 is 273, and P2 is 720. So you got to make sure you put all these numbers in correctly. This is sort of inverted here. This, of course, is the temperature, and that's the pressure, but that's what you have down here. This is the first pressure, the first volume, and the second temperature. And again, that's just solving for V2. So V2 is going to be this. If you solve this correctly, you will get 3.11 liters. And that is your lesson on the basic gas laws. Yes, you do have to memorize these relationships. And I sort of think just remembering this combined gas law can be very helpful in doing that.